Society. Our chapter is based at Mines. We're right down the road. Here with me today is Dr. Mark Lusk. He is a physics professor at the school. Honestly, one of the better professors I've ever had, so I'm very excited to hear his lecture, and I hope you are too. Take it away, Mark.
Thank you, Emily. Okay, final test. Does this work? Up in the back, can you guys hear me all right?
Yeah.
Wow, excellent, okay. I don't know about this little thumping noise, but it's like that. Okay. But I'll give it a try, okay? Well, good evening, and it's a pleasure to be here tonight. I really appreciate all the efforts of the Sigma Psi Sigma Society to have this organized, and I'm excited to be the first lecturer of the series. So let's get started. My research area and my teaching area is in quantum mechanics. I do that at the undergraduate and graduate level, and my focus is on something called AMO physics, atomic molecular orbital physics, and optics in there too. And I declare myself qualified to talk to you about quantum mechanics. How's that? I want to introduce the subject, but really what I want to do is use quantum mechanics to show you that there's something wrong with the way that we think about everyday actions. There's a basic flaw with what we think to be true, and I'm just using quantum mechanics to show you that. That's the goal, okay? So if I say, is quantum mechanics hard or is it just me, I'm going to have to go with me. That's the thought, okay? First, in one slide, without any math, all of quantum mechanics. It goes like this. The quantum idea is nothing more than talking about a discretization of an image. So if I take an image like this and I look at it up close, I got a bunch of little squares, right? So I've quantized the image. I've discretized the image. And that turns out to be what happens to physical properties. They turn out to be also quantized. Things like energy, momentum, position, all the things that you can observe in physical reality turn out to be quantized. Little hunks of energy, little discrete distances that you can talk about when you make measurements. That's the stuff of quantum mechanics. And so it doesn't sound too bad, right? Quantum mechanics is just, okay, you look close enough and you see it. But it's not that part of it that makes it kind of odd. It's the machinery that causes things to be quantized that makes it unusual. And that machinery is what gives quantum mechanics all sorts of names like quirkiness and, no one can understand this and that sort of thing, okay? So I'm not here to talk about quantum mechanics, I'm here to use it, and this will suffice. Now I want you to just say, okay, I get this idea that somehow things are quantized at a very small level. What can we do with that? And here's the question we need to ask. Why again is this so strange? Well, if I do measurements on a normal length scale, normal time scale, everyday life, it doesn't seem to have any influence at all on us. In fact, it does, but we just don't notice that. The measurements at a very small length and time scale show us that some of our most basic, kind of everyday intuitive reasoning is flawed. And so I ask you to be really careful in examining the logic of what you conclude. And all I'm going to do is walk you through your own logic in this lecture. I'm going to give you two thoughts. The first thought is that we like making stories. We create stories to fill in the gaps between the measurements that we make. And the measurements could be things like I observe you or I hear something. That's a measurement. That's what I'm talking about. And in between the data that we get from a measurement, we fill in the blanks. And we make a nice little story. Okay? Now, how does this work? I'll give you several examples. First, let's play a game of tennis, all right? You're on one side, I'm on the other side, I hit the ball your way, here it comes, and you see it coming, right? Do you know where the ball is at every moment? What do you think? I mean, it seems plausible, right? Of course I know where the ball is at every moment, I see it coming my way. But the truth is that your mind does something that you don't realize. It's measuring, using the light coming into your eye, it's measuring the position of the ball about 5 times a second. Okay, so click, 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 maybe a little faster now. And it's causing you to assemble an image in your head that is moving, and you make a little motion picture, and you think the ball is moving in a particular way, and you think that you see it moving all the time, right? But it's really just 5 frames a second. So let's slow down this idea. Let's say that the ball is coming your way, and you close your eyes for a second. Now, not so much that you embarrass yourself and the ball hits you in the face or something, but here it comes, and you have a sense for it. You're already kind of leaning back. You can tell where the ball is going to go, and you close your eyes. Okay, just for a second. But what happens? Okay. What happens is you create a history in your mind of what's happening while your eyes are closed. Now, I call it a history because you're closing your eyes, you're not taking in any sort of data, and later you're going to open your eyes and see what happened. And so you're assembling a history that you can then say, yeah, that's exactly what happened while my eyes were closed. Does that make sense? That's the history, okay? And there are many possible histories, but all you're doing is putting together the most likely history. We always rank these things. And the most likely history is that you understand basic mechanics, and it comes and bounces, and you know about where it's going to come. And so when you open your eyes and do a new measurement, you say, aha, my history was a good guess. What I thought was a plausible history turns out to be right. Now, we don't actually say that. We're like, wow, good. But the point is that you had to do an awful lot in your head while your eyes were closed. Okay? Now, I'm going to slow this down in a sense even more to giving you another example, because it's this idea of many possible histories that I want to examine first. So, this is a true story. Okay, I take out the trash, every Monday night, put it on the curb, go to work. On Tuesday morning, there it sits, and when I come home, I expect to see the trash can there empty. The good folks from the trash company have come and dumped it out. Make sense? Yeah. So what I've done while I'm at work is assembled the most plausible history for the actions associated with that trash can. And so I expect to see it sitting on the curb, right there, all right? But one day I came home from work, and it wasn't there. And I thought, oh, that's interesting. So what do? I immediately down-select from all my big array of possible histories. I knock out the most plausible possible history. And I say, okay, what else do I have? What else happened? What else could have happened? And then I think, I know. My wife came home from work early, and she brought the trash can in. Completely reasonable. It must be sitting in the garage. And then I remembered, no, she's working late tonight. That's not going to happen. She's got this client in, and she's not going to be coming home. Okay, so then I think, knock that one off. Next most plausible history. My daughter came home from school, 3 o'clock. She saw the trash can there. She thought, I'll take this in. Chance of that happening? 0. Okay? That's not going to happen. So I immediately knocked that one off. So then I think, what else could have happened? Where's the trash can? Someone stole it, right? Okay, it's down on the list. It's not my first thought, but someone stole the trash can. My neighbors covet my trash can, okay? And they saw this as an opportunity to abscond with it. And, of course, I'm going to see it next week outside their house. But this is my next most reasonable thought. Someone took my trash can, okay? Right up there with maybe the wind blew the entire thing down and hit it in the culvert or something. It turns out, though, that when I looked around, I found the trash can on the side of the house. And that seemed completely unreasonable to me, and made me come up with a whole bunch of new possible histories of how it got to the side of the house. It turned out that there was a fella that had been working on our house, and he came and was working on the house, but he saw the trash can out front, he saw it was empty, and he was being nice, and he just brought it in. He thought this is where we stored the trash can. Okay, so then you're like, okay, that's the actual history. Unless he's lying, right? Unless he's not, it's something else happened, and maybe he's not even a real person. I mean, you could go on and on, right? You could go crazy on this. The point is that there are an infinite number of possible histories. The only thing you know is there's a trash can. There it is. That's all you can ever say. You can't put any reality in the history that you invent. All you can do is say, I have made a measurement. And that's the first thought, okay? That's what I want you to think about. All of the histories are just ideas that you string together because we all like a good story. Now, it's also a survival mechanism. It's important to be able to make these possible histories, to make predictions. And so there's a good reason why we make these stories. It's just not physically accurate. All right, let's do another one. And what I'm going to do now is make it simpler and simpler. I went from the tennis ball to the trash can, and now there's not really any time involved here. It's just a couple of simple squares. Okay? I have a lower left square, blue, and an upper right square, red. And I show you these two squares, and I tell you, you know, you close your eyes. I'm going to redraw these squares so that they overlap. And you think, okay, I get it. One of these two possible histories. So this is a really simple example, right? No loopholes, only two possible histories involved. And you fully expect to see one of these two when you open your eyes, okay? And then I show you this. It's a Necker cube up here, okay? It's a picture that you can look at and see two different images with, right? So here you have both histories existing at the same time. How is that possible? What's going on here? I mean, is it really two possible histories, or is it some kind of optical illusion? Right? We call this an entangled state. Right? This Necker cube, and if you're looking at it enough and trying to make these images come out of that cube, you can kind of see it oscillating back and forth in your head, right? And I think you guys have all seen this before. So, but the thought here is that this is a representation of what we know as an entangled state of two possibilities. Keep that in mind. I'm going to come back to it, but I need to bring in a second thought. The second thought is that part of our evolutionary development, part of our success as a species is associated with hardwiring in us that makes us jump at finding cause and effect. Right? It's such a valuable thing. The problem is that we assume causation a lot of times when all we really have is correlation. Now, as a survival mechanism, it's okay to overestimate cause and effect. All right? In most cases, I'm a hunter-gatherer. I walk up and I decide to go around the mountain to the left, and I go over there, and there's a big cave, and a bear comes out. Ah, it's like almost kills me. All right, and then I think, cause and effect. I will go to the right next time. All right, that's useful, right? That's a good thing. So we want to take advantage of cause and effect, but we don't want to get so mixed up that we end up misusing that. All right. Correlation versus causation. I push a box, and then the box moves. It's completely reasonable for me to decide pushing the box causes it to move, right? Good. Here's one that's dumb. I eat breakfast every morning, and then the sun rises. Eating breakfast causes the sun to rise. I better eat every morning, right? I mean, I better go for it, all right? So everyone's counting on me. All right, that's completely stupid. It's there's correlation here, but not causation. So here are two examples where it's really obvious. One's right, one's not right. But it's not always so easy, right? You guys know this. How many people have a pair of, like Lucky socks? Right? Okay? All right. Yeah. Thank you. I appreciate that. You were the only one raising it. I just want you to know. So there's this idea. I'm sorry, I don't know what I'm doing it. I know. Cause and effect. I think it's correlated. It's easy to get tripped up, and we allow ourselves to get tripped up, and sometimes it's even fun, like the Lucky Socks thing. And secretly, we believe it's something in our soul says, I do think that this tennis racket, even though it's completely worn out, has been good to me, I better keep it. Or that rock, we start thinking about, last time I had the rock, I did a great hike, I'm bringing the rock, even though it weighs, 20 pounds. Okay? So we do this. I eat my breakfast, and then my stomach hurts. Eating breakfast makes my stomach hurt. True? Maybe after I eat breakfast and I get ready for work, I start getting anxious. Stomach acid. I feel lousy. It's work that's doing it. Or it could be I've got some kind of crazy ulcer. You don't know. But it doesn't stop us from jumping to conclusions, right? Children that watch a lot of TV are the most violent. There's some statistics that seem to indicate that. TV makes kids more violent. Completely reasonable. Violent kids like to watch TV. Reasonable or not? Maybe. You don't know. Right? It's hard to say. That's the point. Let's draw a couple of plots to kind of quantify this a little bit. Over the last 30 years, CO2 in the atmosphere has gone up. That's true, all right? Over the last 30 years, because technology has improved and because we care about the environment, the number of electric cars on the planet has gone up. I plot them together. Is that true or not? It's definitely true, okay? That's definitely true. There's a nice correlation between the number of electric cars and the CO2 in the atmosphere, all right? That's a correlation. Is it causal? I hope not, right? Okay. But definitely that's true. So what happens is you get to the point where you see a correlation and then you want to jump to a conclusion. You want to use that. You want to exploit that knowledge. That's the causal part that's so dangerous. Especially in quantum mechanics, especially where we're headed. All right, let's go back to this Necker cube. I'm looking at the lower left square. What I did was I reached out to that Necker cube and I looked to see which face I actually felt, okay? And I found out my fingers touched for the lower left square, okay? And so I say, oh, the lower left square is there. All right. Did that cause the upper right square to suddenly whoop, go to the back? No, of course not. Now, I'm saying this and you're like, this is so dumb, I get all this. But pretty soon, I'm going to tell you that just the opposite is true. Your intuition will fail you. That's where I'm headed. So work with me on this. You know, build up. Be patient as we work through these little simple examples. Okay. So all I can say is that their positions are correlated, not that one caused the other to be in a position. Right? All we did is said we have two histories, and by putting my hand out on the Necker cube, I ruled out one of the possible histories. I could tell which one was actually the case. Okay. So this seems all very, intuitive. I get all this. And I'm going to give you one more example. And we're going to use this checker example in an increasingly sophisticated way. All right? Eventually, we're going to even turn these checkers into photons of light. But that's a little bit down the road. So I have these two checkers, red and green. Just plain old checkers. And you get a friend, we do an experiment. I take the checkers, I shuffle them up my hand, I hand you each a checker, nobody looks at the checkers. You put them in your pocket, okay? Each of you puts one in your pocket, and you don't know what you got. You walk in opposite directions for an hour. You pull out your checker, you peek at it, it's red. Right? Did you cause your friend's checker to be green? Is your friend's checker green? Yeah, of course it's green. Did you cause it to be green? No, you didn't cause it to be green. Okay, there's a correlation, but not a causal relationship. Okay? Certainly not instantaneously. But in doing that kind of thing, we've taken some things for granted. Now I'm going to drill down just a little bit in terms of logic. Still, there's no math here, but it's the logic that's the hard part. Two things that you do when you examine a problem like that. One is called locality. Okay? Your peek at the checker did not cause something to happen to your friend's checker. Okay? No such thing as action at a distance. It didn't instantaneously change the checker. It's just a down selection of possible histories. There were two possible histories, and you found out that only one was true. Okay? So that makes sense, locality. Realism. The color of the checkers was fixed from the start. Peeking just revealed the color. Now, that also makes complete sense, right? It's in your pocket, and you know that all that hour that you were walking, your checker was the same color. It's just that when you pulled it out, you revealed the color to yourself. And again, it seems very obvious. But these things are not always true. In fact, the basic reality that quantum mechanics shows is that these are not true. Now, I want to give you an example, and Randy, I need someone to help me with that laptop, just for a second. Okay? Yeah, you can do whatever you want as long as you don't break it on account of its mine. So you can turn it around, but what I want you to do is start something. I'm going to have you start a movie just by moving an arrow to it. Okay? Thanks. Okay, we're almost there. I just thought I'd give you a little bit of warning. Appreciate it. So now let's talk about cause and effect and our intuition. This idea of locality and realism, let's take them together. Okay? It's a basis for thinking about cause and effect. It helps us to assign causation. All right, we use these ideas that I see whatever happened is just local right here, and it affects that, and it affects that, okay? And the properties are all there, I'm just stringing them together. Together we call this local realism. And the reason we do that is because, you know, they go hand in hand. If you don't have locality, it's pretty hard to decide that something has a real value before you measure it. I mean, anything could happen. And if you don't have any value at all, then in a sense, it could be getting its value from somewhere far distant. It could be non-local interactions. So let's go through this as an example, this shell game idea. Now you've seen this a bunch of times. I take a pea, I put it under a walnut shell, and I move it all around, and if I'm really good at it, I can trick you. Okay? So here's the thought. Locality. The pea must be under the same shell. True? I mean, that's an assumption. A bad assumption. Okay, that's an assumption. And then you say realism. The pea is always somewhere. It doesn't just suddenly appear when, at the end of the experiment, and in between, it's not there at all. So let's see. Now, Randy, if you could somehow make that happen. There you go. You're good. So this guy's moving it around. The lady is watching very closely. You're watching closely because you think you can figure it out, but it's not showing you the whole thing. Okay? She's watching. Look at her face. Her eyebrows are down. She's thinking about it. It's right in the middle. No. Okay. Now, he tricked her, right? But why is that funny? Why is that fun for us to watch? It's fun for us to watch because we know that locality and realism, local realism, is true. And when someone demonstrates an apparent lack of local realism, it's humorous to us because that's ridiculous. It can't possibly be true. Now we can call it magic and we can say stuff, but in fact, we know it's just a silly game, right? We want to learn how he did his great trick. All right. Is this violating anything here? Let's see. Local realism is not always true, but does it violate cause and effect? And what I mean by that is, does it allow us to do things like, just before I am ready to throw the ball, I see it flying through the air. Okay? Things like that. Or just before I pull the coin out of my pocket, it's in my hand. Now, that would be a violation of cause and effect, right? Or if I do something here and someone in another part of the state learns about it faster than the speed of light can travel. All of those things would be violations of cause and effect. But the experiments that we do show even though local realism is violated, cause and effect is not violated. Okay. Does it allow information to travel faster than the speed of light? Absolutely not. Although a lot of people will talk about this sort of thing, especially in science fiction novels. You know, I read them, I love them, but a lot of times I'm like, no, that's not right. So, what I want to do is walk you through this idea of lack of local realism and show you how real experiments using light or entangled particles like electrons, how this happens. But I'm going to use a pair of checkers, okay? So bear with me on the checkers, it's just a nice construct. I'm going to trade in the simple red and green checkers for these sparkly checkers, all right? So I've worked on these, and I call you and your friend over, and I say, we're going to do the same kind of experiment, but I'm going to claim something to you guys. I'm going to claim that I hand you these checkers, and just like the red and green, you're always going to get the opposite color, no matter what, okay? Once you take these out of your pocket and you detect the color, they're going to be the opposite of each other. And you think, okay, we've already done it, but we may as well. The sparkly checkers are cool. Let's give it a try. Okay? So the checkers have a color before we make a measurement, right? I mean, it makes sense. Normal checkers. Is there something that I can do to these checkers to somehow get around that and have the color not be decided until the measurement is actually made? And then, can I somehow figure out if local realism is false, if there's some way of looking for non-local correlations between these two checkers? So here we go. I'm going to tell you that the checkers in principle can be any color on the color palette, but in practice, I'm going to, just because it's simpler, I'm going to reduce it down to 4 colors. Red, blue, top and bottom, magenta, green, left, and right. That's my idealized palette. And the checkers can be any one of those 4 colors. Now, I want to say that If so far you've been kind of drudging along and yeah, okay, these things will get a hold of you and suddenly you'll be 2 slides in and you'll say, uh-oh, I lost track of the checkers. Okay, so make sure that you know what is going on here and stop me. Okay, bump your friend and make them raise their hand or something because you don't want to do it, but make sure and stop me if you don't know what's going on. Okay, here's the color palette, 4 colors, all right? I give you these checkers and here's how they work. The checkers don't actually show you a color. They have a button in the middle. You push the button and it randomly picks a color, but it doesn't tell you what the color is. Instead, it tells you true or false. It says true if the color is in the top half of the color palette. So red, or the top half of magenta, or the top half of green. Okay? False if the color is in the bottom half. So here are a couple examples. Suppose that I push the button on the checker, and secretly, the checker doesn't tell me this, but it picks red. Completely red. Okay? What's it going to show on the screen, on the little screen on the checker? It's going to show true, because red is fully in the top half. Right? Okay, what if I secretly, by pushing the button, picked green? Then green would give me true half the time and false half the time. Why? Because green is kind of halfway, right? It's a border case. And the same would be true for magenta, 50-50. And then, of course, blue would be false every time. Okay? So now I see how the checker works, and I want to play again. All right? How does this work? You get your friend. I make a special pair of checkers. I tell you that I've linked these checkers together. I've made some sort of special correlation when I was in my garage, and I hand you these, and I tell you, go ahead and check out the nice correlation that I have. You're always going to get the opposite color. Now, this is already tricky because I've got 4 colors to choose from, and I've got a cool button to push. Okay? So you take planes, Maui and Vienna. All right, you guys decide, fight it out. They're both kind of nice, and they're on opposite sides of the planet. That's why I picked those. All right, just about opposite. All right, you decide on a time. You both push your buttons at exactly the same time, or pretty close. Okay, you push your buttons at the same time. You find your button says true. And you're like, okay. Now your friend's nowhere around. You don't know that your friend says false. And then just to make it simple, let's say that you guys don't share your knowledge until you get back to wherever you started, say here in Golden. Okay? And you come back and you compare notes and you say, we got the opposite, but maybe that was just, there's a good chance, there's a 50-50 chance of doing that. So I give you a new pair, and I say, do it again. You travel back to Maui, Vienna, maybe you trade places. Okay? And you, this time, make a measurement. You get a different measurement. You're like, different measurement. But your friend is saying the same thing. They got a different measurement. You're still anti-correlated. You have the opposite result. You repeat this a lot of times, like maybe 10,000 times, okay? And you tabulate the results, and you find out that you always got the opposite result, the opposite color. Maybe it was magenta and green, maybe it was red and blue, doesn't matter. You always got the opposite result. There's 4 possible histories, but you only ever see 2. Now, why is that? I mean, what are the 4 possible histories? There's true, true, right? You both saw true. False, false. True, false, false, true. But you only ever see 2. So somehow, there's a correlation involved in the possible histories. And somehow, you've already down-selected from 4 possible histories to 2 possible histories. In fact, I've down-selected it. How did I do that? I down-selected to 2 possible histories by doing some crazy stuff with the checkers before I ever handed them to you. When I said I did something special. This is the correlation, okay, that I'm talking about. So, what's going on? Maybe your checker is controlling your friend's checker, right? Maybe it just happens kind of fast and you don't realize it. Maybe you're super duper lucky and you just always do this. Maybe there's ESP involved. We invoke this kind of thing all the time. Maybe sinister forces are, at play here and you didn't realize that some higher being is screwing around with your mind because it doesn't want physics to prevail. How are these 2 possible histories being ruled out? Why is it that you're always anti-correlated? What's as simple as that? I tricked you. I completely tricked you, right? That's the simplest thing. That's what you should assume, just like the guy with the little walnut shells. All right? How did I trick you? Maybe I hand you these checkers and I like make noises and notations and stuff, and you think, ooh, these checkers are very special, never the sparkles, okay? And you got the button, and then underneath, sorry, I really don't, I think this is anti-causal something. Okay, I'll be careful. So somehow, what is really going on is that all I did was gave you a red checker, okay? And the thing spins and the lights come on or whatever happens, and it always just says true. You got a red checker and it's gonna come up true every time because red is in the top half. And your friend has a blue checker, and every time they push the button, they're gonna get a false. And then when you come back to see me, I just kind of, every once in a while I trade. You get the blue, he gets the red, and then you're like, oh, I got a different reading. Okay? That completely makes sense, right? So that is the most plausible explanation, not that physics is somehow different than what you thought. All right, that would be realism. The colors are there to be revealed. It's just that you're getting duped. The colors exist before the measurement. And so you think about it, you say, you know what, I got a better idea. I can make a system of checkers that can't be tricked in this way. All right. New checker system. 2 buttons on the checker, okay? And the sparkling ones. All right, so the button 1 is the same button you've had before. True, false. True if the color's in the top half, false if the color's in the bottom half. But now you have the second button. You push that one instead, and it does almost the same thing. True if the color's in the left half, false if the color's in the right half. Okay? And you can push either button. So you only see true or false, but you get to pick which button you are going to test with. Now, let's test this. This is kind of a hard concept. You've got this 2-button checker. You push button 1. That's the up-down button, just like we've done before. And the secret pick, just like before, is green. And you see that half the time it says true and half the time it says false. Look up the color palette. Green is a border state. Okay? Good. What happens if you push button 2 and this secret selection process, the random selection process, gave you green? Then you would always get false. Now see, that's different. Now you're in control. Unlike the case where you only had one button, you get to decide which button you're going to push. And so right there at the source, after you leave me, you're in control of the experiment. And you see, for green, suppose that I secretly made your checker green. You can get 2 different answers, right? So here we go. I give you the 2 checkers, the upgraded checkers. You and your friend are excited about this. You're going to disprove me in my theory. And you take planes to Maui and Vienna again. You're getting sick of these places. And because you've been there like 10,000 times. And you pick a button at random, and your friend picks a button at random. And you find out that when you get back, that you're anti-correlated. Mine was, yours was true, and your friend's was false. And now it's just one time, so you do this another 1,000 times, you tabulate the results, they're always opposite. Okay? This should really bother you. Why should this bother you even more than before? Let's go through it, okay? Suppose that I was trying to dupe you, and again, it was just red and blue. The same would be true if I did the argument for magenta and green. So red and blue, okay? And if yours is really red and your friend's is really blue underneath, and you got this 2-button system, suppose you pushed button number 2, okay? That's the left-right button. Then blue is up there, is a border, right, for the left-right. Blue is a border state. And so blue is going to give you a 50-50 probability of getting true and false. They're equally probable. That means that when you push, if yours is really red, and red's a border state too, of course. If you push this button number 2, and yours is really red, you're going to get true 1/half of the time. And your friend is going to get true 1/2 of the time, and 1/4 of the time, you guys are going to match up. And so 1/4 of the time that you do an experiment, you should both get true. And 1/4 of the time that you do this experiment, if you're both pushing button 2, you should get false. Now, you both should get false. Now, it's true that that's not going to happen all the time. But remember, you're traveling a lot. You're doing this thousands of times. So all you have to do is call out all the cases at the end where you both chose button number 2. Okay? And then you look at those, and darn it, you should see that a quarter of the time you're both getting the same true, and a quarter of the time you're both getting the same false. But that never happens. The colors seem to be not predetermined. If they were predetermined, this would bear out, but it doesn't seem to be true. So realism is violated. The colors aren't in existence until you actually push the button. And yet, there's an anti-correlation. Is this some kind of cause and effect? Checker pairs are always anti-correlated, all right? How can that be true? The colors are being chosen at the time of the measurement. But what does time mean? Maybe there's a more devious trick that I'm playing on. Maybe it's not just a matter of realism. Maybe it's a causal issue. Right? Maybe what I'm doing is, embedded in these checkers, there's a tiny little antenna system and a little cell phone, okay? And as soon as you push your button, whatever it is, it says, you got a true, and it just sends a signal over to Maui, and that one comes up false. Okay? It only takes a 15th of a second for light to travel around, halfway around the world. So that's pretty short, right? Maybe there is a causal issue here. I could still trick you. And I want to pause for a second and point out, what am I doing? I'm trying to rule out issues. I'm trying to rule out loopholes. Okay? I'm looking for a loophole-free test of this system. I want to get rid of all of these crazy possibilities. So definitely have to test this. So I take you guys to SpaceX and we plan a trip. One of you goes to Luna, one of you goes to Mars. Personally, I would try the Mars thing. First to Mars, that'd be cool. So off you go, all right? Now, why are you doing this? Because it takes 3 minutes for light to travel between Luna and Mars. So that's pretty easy to verify if there's some kind of little cell phone involved. And plus, the antenna would have to be something pretty cool. All right, so to fit in there and transmit between those two places. So now you've got these 3 minutes. As long as you're making a measurement within a minute of each other, you're good. And that's something we can easily do. So you do this and you find exactly the same thing. 10,000 trips later, you're ancient but happy that you've proven something, still anti-correlated. Okay? All of this causes you to conclude something. Either you come up with a completely new theory, yet another loophole that you have to close, or you give up. Now, there's no way to say that I've gotten rid of every loophole, right? But you have to go through it, your friends go through it, you examine the evidence, and finally you say, we've closed all the loopholes, and we still see the anti-correlation. In fact, that's what people do in real experiments. There's no color before the measurements. The measurements are always anti-correlated. There's no communication between the two checkers, and yet they're always like this, of opposite color. We say that this is an entangled state. These checkers exist in an entangled state, and that there's no way for us to separate them. The measurement of one is going to do what? How does that work? What's happening is you're down-selecting. The measurement of one of the checkers down-selects the possible histories. You measure red, and all it's saying is, okay, there were a lot of histories, but now the other one has to be blue. They're always opposite. That's all that's going on here. This idea of local realism being violated doesn't say anything about cause and effect. It just says that these are always going to be anti-correlated. That's the idea of an entangled state. Now, I can talk all about this in terms of the physics and the photons, but you've got, in a nutshell, something that has bothered people for decades. How does this actually work? And whether it's checkers or photons, it's the logic that we fight. It's the logic that you can have things that are anti-correlated at a distance. And in fact, the basic logic is that you don't like the idea that locality and realism are being violated because we lean into that so much every day. Maybe something's happening faster than the speed of light. Right? I guess that could be possible. But remember what you're doing is you're doing the measurement, and then you're going back. You don't know what your friend's measurement was until you get back to golden. And so this idea of somehow you instantly knowing what your friend's is and having the two measurements side by side, that's a bad picture to have in mind. All you're doing is making a little table and comparing tables when you get back. Okay? This is just correlation, and that's why I say it's correlation and not causation. Okay? All of this is called, because it's quantum mechanics, and because these states are entangled, and that's the stuff of quantum mechanics, we call this quantum correlation. But it's no big deal. It's still just correlation. All right. Now let's trade in our checkers. Instead of having the checkers, the classical objects, we use these photonic energy bundles. And what I mean by that is that I have a problem saying particles. Okay? It's hard for me. And that's because of the work that I do. I think of these little bundles of energy as being disturbances of a field. Like if you hit water, you hit water with a rock and you see a disturbance in it, the water disturbance is what I think of as a little packet. And maybe I can make a wave that moves, and I think of that as a little bundle of energy. But I don't like the idea of thinking of a little nugget as just moving by itself. I think of it as the disturbance on the pond. Okay? But it's still useful to talk about particles as a construct. A little bundle of energy is harder to say than a particle. So let's just say particles. And so I'll deal with these little particles of light. Now, there are a lot of them, and so this is a good system to use. This is a better system than me sitting in my garage slaving away on these 10,000 different pairs of checkers, right? So you know, we've got 10 quadrillion of these things going into your eye every second. That's as many, you know, ants as we have on the whole planet. Okay, so there are a ton of these things to draw from to do your experiments. And there's something else that is very useful about these photons of light, the particles, that isn't true for the checkers. They have a feature that I'll call it, they're anatomically correct. They do something checkers can't do. And it goes like this. Light has polarization. So I'm going to trade in my checker colors for polarization. Okay? So don't think of the colors of light as being what I'm using here. I'm not. Now you know that light is oscillating back and forth, right, as it moves. And it oscillates in a direction perpendicular to the direction of its travel. And so if it's horizontally polarized, you can think of this as going back and forth as it goes down this axis. Okay? Vertical polarization is just the opposite. And so instead of red and blue, I'll say horizontal and vertical polarization. So I put an H and a V over here. But if I take the horizontal and vertical polarization, I can build two other, we'll call them colors, right? Two other polarizations. I can build the magenta and the green from them. That's something that I couldn't do with the actual colors that I used for the checkers. All I have to do is phase shift the vertical polarization. Maybe I hang it back by 90 degrees and I add it to the horizontal polarization. And what I get out is a spinning polarization, right? Circular polarization. Now, if I push the vertical polarization ahead by 90 degrees, I'll get a left circular polarization. So I can build right and left, the other two colors, out of my horizontal and vertical polarization. Okay? In fact, I can go the other way, and I can build vertical and horizontal polarization out of these two. Just the same idea, adding and subtracting. All right. Why is that useful to us? Let me explain the basic idea of this experiment. There's something called spontaneous parametric down conversion. It was discovered decades ago, but really perfected in 1995. You know, not so long ago, right? Less than 3 decades ago. And the thought is this: I send in one particle of light, one photon, into a crystal, and what comes out are two particles of light. Each have half of the energy of the original, and they have opposite polarizations. And so I can get these two particles of light to be horizontal and vertical polarization. But that's exactly what I wanted to do in the garage with the checkers, right? Because now I have this simple crystal, okay, this beta barium boride oxide that I can just set up a block of. I send a flashlight into it, and magically out the other side comes this light that's entangled. And if I have that, then I can funnel one over to Maui or Luna, and the other over to Vienna or Mars, and I can do a little check on them. And I find out that they're always anti-correlated. So this is the realization of the checkers that we're talking about. Now what's interesting about this is that besides just, wow, that's cool, you can do this instead of the checkers, okay, is that because of this relationship between the horizontal, vertical, and the right-left polarizations, I can entangle these photons, and I have this entangled pair of horizontal, vertical polarizations, okay? And I can mathematically describe it as right and left circular polarizations too. So if I tell you I've got an entangled pair of polarizations, you should say, I bet you, if you tell me horizontal and vertical, I can just rewrite the math, and I can also say just as easily it's right and left circularly polarized. There's no way to tell the difference. They're mathematically the same. And that's important because that is what I use with the two-button sequence. Okay? Because now what I can do with the two-button sequence is I can measure for right or left circular polarization or horizontal vertical polarization. Those are my two buttons. Okay? It's the same photon going out. It's that I can make two different measurements, right, left, or horizontal vertical. So there's your checkers. Okay? And when you do this, you find out, just like with the checkers, we can tell them they should have guessed this because we already did it with Luna and Mars, then that you see this anti-correlation. And this was only done, the first, what is called the loophole-free test of this lack of local realism was only done a couple of years ago. In fact, there was a big race. Okay, people know about this. It's a friendly but fierce competition between the folks at Delft and folks up the road in Boulder at NIST. And what happened, sadly for our team, is that there's like a 2-month lag on our side. But okay, they showed something a little bit different. All the knowledge is good. The bottom line is that in the fall of 2015 was the first loophole-free test of lack of local realism. Okay, now these things are separated by about 1 kilometer at Delft, and I think it was a little bit less than that at NIST. It was just kind of around the corners of a building, so I'll say maybe like 300 meters. Just last year, there's a Chinese group that did this via satellite, and so they found that they could separate their photons, entangled photons, by 750 miles and still show that this anti-correlation exists. So this is kind of like the Vienna Maui thing, right? And on its way to being something that you can do across space. It's almost in the realm of science fiction to show that entanglement exists at this kind of distance. So this is an established fact now. We understand what entanglement does, and we understand how it affects this notion of local realism. It shows us that local realism can't be true. Okay? What we say, physicists say, is that Bell's inequality is satisfied because there was a mathematician named John Bell who made up an inequality and said, you know what, if you ever violate this mathematical statement, then I can tell you that local realism can't hold it. People apply that to this situation of the photon entanglement and show that yes, indeed, Bell's inequality is violated. All we're doing, though, is down selecting. We're down selecting the correlated histories, and then we're choosing one of the correlated histories. All the other histories were never possible. And all the idea is that you reach out and touch the Necker cube and see which one it is. That's it. There's a lot of mysticism around this. This is not causation. No fair instantly sending messages across the galaxy, even though people say that. In fact, there's an important phrase that is invoked all the time, this thought of quantum teleportation. It sounds great, right? It's a real thing. People write papers about it. It's not instantaneous either. There always has to be a classical communication that travels at less than the speed of light, even though we call it quantum teleportation. Okay? There's something called ghost imaging, which is awesome. It sounds so good, right? Ghost imaging in terms of entangled pairs of photons. And the thought is that I'll send photons of light into a nuclear reactor where I don't want to go, and then the other photon of light over here will show up on a screen, and whatever's happening to that photon will be correlated with this photon, and I'll see an image of the inside of the reactor. Okay, ghost imaging. That sounds really good. It doesn't actually work that way. Okay, that's how people promote it, but it's Whatever is happening in terms of the this ghost imaging concept can be described classically. It doesn't need to have a quantum correlation to do that. So it's another height. Okay, it's often invoked in science fiction novels. People try to tie it in with ESP. You know it's true, and even things like the Force. Sorry, doesn't pan out. This is a simple idea that shouldn't be extrapolated into. Well, okay, it's not a simple idea. It's a hard idea that shouldn't be extrapolated into more than it is. That's the thought. Okay? And yet, it's really cool, right? This is a new idea in terms in the rate at which science evolves. This is on the frontiers of science. And so what I suspect is going to happen is that folks that get into science like now, okay, over the next decade or two, are going to be the ones that turn this from, wow, now we really understand how the world works, to let's exploit this and make some new technologies. And if you're out there and you're thinking that you might go into physics, you might be one of the people that do that. With that, I'll close and answer any questions you might have. Thank you very much.
Again, so thank you to Mark Lusk. That was a great talk. I hope you all enjoyed it. If you enjoyed this one, we have another Pi Sigma Science talk on April 5th, also at 7 p.m. Right here, that one's going to be on multi-messenger astronomy. It's going to be about gravity waves and neutron star mergers and a lot of really cool sort of astronomy stuff. So if you liked this, please come to that one as well. And I'll give it back to Mark for, if you have any questions, please come ask him. Also, all of our contact information is on the pamphlet you got.
Okay, so this is I've got a microphone and you're sitting way back in the audience. It's kind of a tough thing to decide that you're going to ask a question. Who wants to go first? Yeah, I wouldn't either. Yeah.
So the popular press has made a lot of the possibility of, some experiments have. Somebody has actually changed the state of a quantum entangled bit in this case. I think it was the Chinese, but perhaps not. One that was in the satellite, one that was on Earth.
Right.
They managed to change. How, A, can you explain what that means, and B, how does that not communicate information?
Okay, so yeah, it's a good point. So here's the experiment, and it's except for the cool satellite part, it's just like the checker thing. So what it is that on one side, I do a measurement, and when I measure, say I'm measuring with right-left circular polarization, I measure that photon, and I get right circular polarization. So have I affected that system? Absolutely, right? I've affected the system. But what I didn't do was go over and manipulate something 750 miles away. All I did was measure this photon. Now, in measuring the photon, I reached out and touched the front face of the Necker cube. And so I down-selected from the possible histories to one possible history. And as soon as I do that, since there's only one possible history, the other photon has to be of the opposite polarization. Now, I don't know that. I don't know what that polarization is over there. I haven't communicated with them. They haven't sent me any information. It takes the speed of light between us to communicate information. And so if they then do a measurement, right, they still have to do a measurement. They do a measurement on theirs and then call me and say, yo, we got this, and we compare notes and we say they're anti-correlated. No speed of light has been violated. So it's such a fine line, right? You agree that they're anti-correlated, but have I done a causal, have I caused something to happen over there? No, they still haven't even done their measurement when I do mine. They do their measurement and they find out that because I've done my measurement, there's only one possible history. They're going to get something that's anti-correlated. it's, I can tell you're not satisfied with that. Ask me a follow-up question.
Well, so I've got a couple of follow-up questions. One is trying to square up what you said, which I suspect is true, with what I thought I read in the popular press.
Yeah.
The other is, if I touch the negative view, if I push the button, do I not now know what color the other checker is? An example.
Yeah, I can anticipate that, right? I can anticipate that color when they do the measurement. But be careful, I can't say that it has a color because no measurement has been made. It doesn't have a color before the measurement. So no fair saying, I touched the front face, the back face, is therefore something that they're going to see. Not until they do the measurement. That's another subtlety, right?
Am I not now then predicting the future?
I am predicting the future, but I can throw a ball up and predict that it's going to come down. Yeah. It's not always true, but I can predict it. As far as the popular press goes, I stand with what I said on the Chinese experiment. I've had, and maybe you've been in this position too, people will interview me about research, and then they will write a nice article, and they're writing it for not the audience that I normally see, and they assure me that they're saying things that they have to say in order to make it palatable to the audience. And I read it, and I go, yeah, but it's not true. Is that a problem? No, that's okay. They don't say that. But it could be that something was a little bit misconstrued, an honest misconstrued. I'm guessing. But if you maybe go back and look and see, did they say that information was transmitted instantaneously? I hope not. I hope they didn't say that. Or that they caused something to happen 750 miles away at faster than the speed of light. Boy, that definitely shouldn't be true. Okay. Let me get a follow-up question here. Yeah.
So as you present this, in a quick summary, it sounds like if you have two possible things that happen with these photons or with these checkers. If you measure one locally as A, then B must be at the other end. It seems almost that it's not a useful thing to do to even talk about entanglement.
I think you have an important point there. Okay? It's so cool, right, that immediately you want to jump on it and say, I bet you we'll be able to use this. I don't know how many science fiction books I've read where you send entangled pairs out and people use these parsimoniously to communicate back to Earth that's 10 light years away, because you only have a few million of these entangled pairs. It's just not true. It just doesn't happen that way. Now, it would be bad of me to say that this is useless, because history says that whenever people finally understand a piece of physics, technology follows. I'm just not going to predict what that technology is going to be. Is that fair? I agree with your assessment. I think a lot of hype is being made about it, but the real hype is lack of local realism. Wow, how important is that? How many millions of years has that been around? Well, maybe not that long. Thousands of years have we thought that that's probably true. That's the real thing. Did I answer your question, or at least address the idea?
I think you did. A quick follow-up then, why is it even relevant for the Chinese to extend the separation to 750 miles as opposed to a couple of kilometers?
Yeah. It's even more loophole-free, and plus there's a satellite. Really. And which one captures your imagination? Pictures like this where people talk about, and it's true, people talk about action at a distance and things like that when they see pictures like this. It just captures the public imagination. There's no reason to do it beyond that, except that what the thought would be is if we can use this sort of thing somehow technologically, say in terms of quantum encryption, okay, quantum communication using satellites. Maybe it'd be useful to have this idea of being able to keep track of the quantum correlation. But beyond that, no.
Thank you.
That's not meant to be a downer, it's meant to be realistic. Now everyone's sad. Especially the people that like yoga. Sorry. Yeah. What else you got? Other questions? Yes, ma'am. Oh, okay, that's a great question. Why is local realism even used if we know it's flawed and inaccurate? Well, it's the same reason that we use classical mechanics, because it works really well provided that you use it in the right setting. Now, I don't need to do quantum mechanics in order to throw a tennis ball around, for Pete's sake, right? That's really cumbersome, it takes a lot of work. So, is classical mechanics true? Absolutely not, sorry. You know, it's not true. Newtonian mechanics, no, right? That doesn't work. Except, it's a great approximation, right? It's an excellent approximation when the length scales are large and the time scales are large. So, your idea of local realism, let me ask you this, have you ever run into it in your daily routine where you're like, oh shoot, another object has just appeared in front of me, darn it, or something like that? Or you pull out a pair of slacks out of your closet and you're like, they're brown today, I don't need that. Okay, that would, you never had that happen, right? That's the point. Right? Every day living, we don't realize that this is just an approximation. That's all. But once you realize it, maybe you can exploit it. Question? Yeah.
Why are the photons entangled? What about the photons makes them entangled?
What about the photons makes them entangled? Yeah, it's a good question, and I'm thinking of a way of answering that that's not mathy. Let's see. It's good. Okay, maybe I can say it something like this. If I take a rock and I stick a firecracker in it, all right? And I light the firecracker and I throw it up in the air. Then the firecracker goes off and the rock breaks in two pieces, right? Now, there's something, I'll use the word entangled, but there's something that is entangling these two in a different way. There's momentum that's being conserved, right? So they split apart and it's all crazy, but definitely they are dependent on each other in a certain way, right? And the same would be true if you and I sat on the ice and pushed against each other. Our momentum is conserved. So there's this idea that a dynamical process can cause two things to be dependent. And what happens is when this photon of light goes through this beta barium boride oxide crystal, when it goes through that, it goes through, and I'm sorry I have to say it this way, a quantum mechanical process that actually splits the light into two bundles, just like you and me pushing each other back from the ice. It splits it into two bundles, and these two bundles are quantum mechanically, that's the quantum mechanics part, are quantum mechanically entangled. Now, what I would say is that you can go through the math and you can make this prediction, and then you can do the experiment. So, in a sense, all that really matters is the experiment, right? The measurement itself. I think I better stop, or else I'll just start making stuff up.
Hey, Mark, how about I give you a bag and I say it's got two severed hands in it?
It's got what?
It's got two severed hands in it. And there's no reason why they both have to be, one has to be right, one has to be left hand, right? But then I hand you a bag and I say it's got your two severed hands in it. Then they're correlated.
Okay, I'm going to disagree with you.
A single person and take hands, then they're not necessarily.
Oh, okay, I'm slow on the pickup. You're addressing her question.
Sorry to separate them, but I've got to get them apart.
Okay, it's not bad, that's good. It's a little different than, I would say that, Alex, I know you know this, it works a little different than that in reality, but that's a good analogy. I mean, the difference would be that because you could have a right and left circular polarization, I'd say that it's just as likely to look in and see 2 feet. But otherwise, that's not bad. So I think Professor Flournoy's point here is that if you do this spontaneous parametric down conversion, these two things are coming from one body, right and left hands. And so it shouldn't surprise you that there's some sort of special properties associated with their relationship. Is that close? Bag of hands. You're a little sick, man. All right, what else? I wish I knew what I was doing there, I'm sorry. Yeah. Oh, wait. Let me go. He has his hand up first. Yeah, go ahead.
Hi. So you mentioned that the other histories of the particles were never possible. Was that because of block theory of time? Or is that related to a different process?
You said the block theory?
Block theory, yeah.
Like BLOCH, that theory?
That time happens all at once.
Oh, block theory. Oh, no, different way, like with a K. I'm biased by something that happens in condensed metaphysics. Okay, so a block theory of time. Let me think about that. I don't think we need to invoke that. No, I don't think it's a good question, but I don't think that is what's going on here.
Then what makes the other histories not possible?
It's back to the bag of hands. I'm stuck on that. It goes like this, that it's that I just don't create. I don't know how to create two particles that have the same polarization. And so it's impossible for me to create them in the first place. Now, I can create all sorts of different combinations of particles, right? It could be right and left, it could be horizontal, vertical. In fact, there are combinations in between. But they're always of opposite polarization. I can't ever make those other particles in the first place. So I know they don't exist even before I make the measurement. It's more like that. Does that make sense? Okay, so this is a good question. I talked about single particles, or two particles at most, being entangled, right? I have two particles being entangled, but in fact, entanglement happens all the time, right? It's not generally involving two particles. It could be millions of particles. I mean, everything is entangled. In fact, measurement theory, a big part of measurement theory is that something is happening. Suppose that an electron is doing something, and I want to see what it's doing, and I send it through a measurement device, and it becomes entangled with my measurement device. And that entanglement works its way up into a macroscopic state, and then it moves a dial, and I see the dial. And so even things as simple as a basic measurement can be associated with entanglement. It's all around us. It's ubiquitous. It's just that what I was talking about here is working very, very hard to isolate the entanglement so that I can understand it. I think your point is well raised. I'll give you another example. In quantum computing, there are a lot of folks that think that we'll be able to use this quantum correlation to help advance quantum computing to make it more powerful. Maybe it's some sort of parallel processing that would be possible. Now, I don't know how that would work. I start thinking about back to the original point about cause and effect and lack of superluminal speed, right? But there's certainly a case where people are looking at it. Can we use quantum correlation in quantum computing? And another one would be in things like condensates, those Einstein condensates, Clairaton condensates. How are these things correlated? Can you make macroscopic states? Because I can make condensates that, I can make a liter, right? And but I can make a lot of a condensate, and then I can have quantum correlations in this macroscopic quantum state. So maybe that's a good example. I could have macroscopic quantum correlations in a condensate. And that's yet to be explored. What else? Okay, I think we'll stop, but I'll stay down here, and if you have any other questions, please come down and see me. Thank you very much for your attention.
I did, and I was like, I thought it was pretty good.